Hello. So I hope all of you are having a good morning or evening, depending on where you are. So I want to say hello and welcome to our webinar to help you get the most out of your HOMER Pro trial. The focus today is on demonstrating some of the software's most useful features, as well as showing you how to get help for your analysis. My name is John Glassmeyer, and I'm the Director of Energy Engineering at HOMER Energy. My focus is on training users to use the software, that is, I conduct trainings, as well as consulting, in which we apply the software and our expertise in the marketplace. So I'll start by providing a bit of background on the software. HOMER Pro is a tool for rapid assessment of least cost solutions for clean, reliable power. It allows you to mix conventional resources, such as diesel gensets, with renewable resources, such as wind or solar photovoltaics, along with storage, such as batteries and load management, including things such as demand-side management and energy efficiency. Now, HOMER Pro lets you gain insights into the microgrid market. We typically divide this market into 4 segments. 1. Energy access and village power. This market focuses on bringing electricity to areas that currently have no power or limited power from a part-time diesel. 2. Island grids. This is really any remote or isolated community with an existing 24-hour grid, typically powered by diesel. It includes both geographical islands, such as St. Lucia, or the many inhabited islands of, say, outer Indonesia, as well as electrical islands, such as the wind diesel grids in Alaska. Number 3, unreliable grids. Microgrids provide an excellent alternative to frequently used backup generators, as are common in many parts of the world, for example, India. And number 4, resilience. Now, even in places with more reliable grids, outages can have a very high cost, particularly for places with critical loads, such as data centers or research facilities. There's also very strong potential for microgrids for emergency response and reliable power during and following extreme events, such as the 2012 Superstorm Sandy event that affected the northeastern United States. Now, HOMER Pro is an excellent tool for modeling and gaining insights into each of these major market segments, and really any system where you need clean, reliable, distributed power. HOMER Pro is designed to model all of the major components and technologies common across these market segments. Now, HOMER Pro models a range of loads, including electrical loads and thermal loads, as well as hydrogen, and includes demand-side management and energy efficiency. It can also model a range of generator options, including reciprocating units, turbines, fuel cells, and they can run on just about any fuel, including diesel, natural gas, hydrogen, biomass or biogas. And we can also model renewable generation options, such as solar photovoltaics, PV, wind turbines, hydrokinetic or tidal turbines, and run-of-river hydro. And we can model systems interconnected with the utility grid, autonomous systems, and systems that connect to unreliable utility grids. Now, in terms of storage, we model a wide range of battery technologies, including flywheels and more. And we also model combined heat and power and hydrogen storage systems. So the HOMER software enables you to gain these insights by its approach to modeling. HOMER Pro uses an approach that combines simulation, optimization, and sensitivity analysis. Simulation in HOMER Pro uses, by default, an hour-by-hour energy balance to dispatch the components in a HOMER model to ensure that there is adequate energy supply available to meet the load at all times. This simulation is based on a chronological dispatch and is critical for modeling microgrids. It's also necessary to accurately capture the technical and economic performance of these systems. Now, although HOMER Pro typically uses an hourly dispatch, it can be used to model systems at time steps down to a minute. Optimization in HOMER Pro allows you to rank different simulations by the total cost of ownership, which is also called net present cost, or NPC. In that regard, you can think of optimization as a set of simulations. You could imagine simulating many different systems with different amounts of solar photovoltaics, for example. The optimization layer would simulate all of these different systems, and allow you to compare them. Now, by trying a lot of different system designs, you can find the design with the lowest cost. Now, we've recently enhanced optimization in HOMER Pro with our optimizer, and that helps HOMER Pro to find the low-cost system by automatically sizing PV, battery, wind turbines, and system converter for you. If you haven't tried it, the new optimizer makes optimization faster, simpler, easier, and more robust, which we find leads to less user error. Now, just as optimization is a set of simulations, sensitivity analysis is a set of optimizations. When we perform a sensitivity analysis in HOMER Pro, we're exploring how the optimal design, that is, the things that a designer can control, change when we change things a designer cannot control. For example, we might ask, what if the cost of fuel goes up? Does this change the optimal design, or does this change what choices the designer might make? So now, I'd like to do an example to show you how easy the software is to use. So let's start with a quick overview of the user interface. Anytime you open a model, you'll start here on the home page. And the home page is part of the design view. Anytime you're in design view, you'll be doing just that, designing your model. I think it's useful to get some results quickly to show you the power of the software. So with that in mind, we'll start with the newly upgraded wizard. This is a great way to start a model and quickly jump into understanding the results that you can get out of any HOMER model. The wizard streamlines getting inputs into the model and really shows off the power of the optimizer in HOMER Pro. So for today, we'll model an energy access mini-grid in Tanzania. So I'm going to put in the name, Community Mini-Grid System, and we can pick a location. So I'll put this in Tanzania. There we go. And HOMER automatically sets the location and will download resources for you. Now for the load, let's select a community load. And we'll make an autonomous system that is not connected to the grid. We'll have a generator. We'll use the default price assumptions. And let's model it with solar photovoltaics, PV. And finally, the battery. We'll model this with a lead-acid battery. Click Next, and then Calculate. Once you click Calculate, HOMER Pro will use the optimizer that I talked about earlier. And it will use this to find the optimal system across a range of system types. So as the optimizer is working, you'll see that it's simulating a range of systems. This plot shows the net present cost of each system being considered. And you'll notice that it's slowly getting better, and it jumps up periodically as it tries different system types. So once we get some results here down in the optimization table, you can see that the lowest net present cost, the one at the top, is automatically identified and listed at the top of the list. So this winning system is a hybrid design. It has 25.4 kilowatts of PV, a 24 kilowatt genset, 79 lead-acid batteries, and a 6.75 kilowatt converter. HOMER's also identified other system types. This includes the 100% renewable system, which is based exclusively on battery and PV, the battery diesel system, and the PV, what we call diesel fuel saver, as well as the diesel-only system. And you'll notice that the battery and PV component sizes are dramatically different across these different categories, yet the HOMER Pro Optimizer automatically found those for you. Now, before showing you how to adapt this model to your particular application, I'd like to take a minute to show you some of the neat features and outputs. So the outputs from the software include a lot of tools for getting high-level as well as detailed results. For example, you can customize the results that are summarized in the sensitivity and optimization tables. So to do that, you click on column choices, and you can add in columns, say for the total CO2 produced. Okay, and here it shows up. You can also take these and export these tabular results to an Excel or other spreadsheet software by clicking on the export button here. And let's call this a sample export. And let me pull up well here. How do I get into, there we go. And let me go into there. There we go. So here's the sample export. We'll open it. And here you can see all of those results are now plotted out in this comma-separated value, CSV comma-separated value spreadsheet. So let's close this. So really what I wanted to show is that the software is really designed to easily interface with other software, both here on the outputs, and you can actually also use it with copy-paste on most of the inputs in the software. So in this little discussion, we've been focusing on the ranking of these simulations, that is, the optimization table. Now let's take a deeper look and dive into the simulation results. To do that, we select one of these simulations. Let's say the one with the lowest net present cost here at the top of the optimization table. By double-clicking on one of these systems, we go into the simulation results. And this allows you to see, for example, the cost summary, to see where you've spent your money, the cash flow to predict how your cash will flow over the 25-year project life that we've assumed, the electrical tab, which shows where electricity is produced and used over the simulated annual chronological dispatch. You can also get a summary of the fuel, as well as summary statistics on renewable usage and summaries of emission production. You'll also have a tab for each component that provides useful summary statistics about the performance of each. For example, the genset, or the battery, or the PV, or the system converter. Now, I've mentioned that the simulation includes an annual chronological dispatch. And I'd like to reiterate, this is critical for accurately modeling systems where you want reliable power, particularly those with storage. And I'd like to show you what chronological dispatch means. So we'll click on this plot button. And this loads up the time series detail analysis. So it starts with the AC load, and you can overlay, for example, the PV power output. There it is. The genset power output. Where is it? Right there. And even the battery performance. So I'll put the battery performance. I like to use the state of charge in the battery, and I'll put it on the second set of axes by clicking the right-hand checkbox. And you'll see there's another set of axes that appears. Oh, I clicked it twice. Let's get it back up there. There we go. And you can zoom in. So if I click and drag, you can zoom in to see the dispatch for a few days or look at the whole year. And you'll notice that HOMER is automatically using the battery, using the generator, and calculating the renewable performance all over this whole year. And there's a lot of computations to ensure that you have sufficient power at all times to meet your load requirements throughout the year. There's a bunch of additional plot types to look at and go through this data, but in the interest of time, I'll let you explore those on your own during your free trial. Now, when looking at the economics of these types of systems, it can also be useful to determine the payback or internal rate of return. HOMER Pro does that for you. So if you'd like to know the payback for this system, you need to compare its costs against another system's cost. Now for a remote system, so we'll click the compare button. For a remote system, this is typically the 100% diesel system. So I'll find that, select it in the list. And as you can see, by this comparison, the lowest cost hybrid system design we selected originally has a simple payback of 3.9 years against the diesel-only system. Now, this has given you a taste for the sorts of outputs and tools that the HOMER software provides. I want to give you a quick tour of how to modify input parameters. So I'll close out of this, so you can create your own models. So you'll need to switch out of the results view, back in the design view. And I want to take a minute to show you that you'll notice the wizard automatically built a schematic containing the selected components and loads from the wizard. And you can either add new loads, here using the load ribbon, or new components or technologies using the appropriately labeled ribbons respectively, or you can modify the components by clicking them directly on the schematic. So let's have a look at the generator in our schematic. You can see here that the wizard used what we call the auto size generator. This auto size generator automatically sizes this generator to 1.2 times the peak load. And this ensures that you have sufficient generator capacity at all times. You can also specify the install cost, the maintenance costs, using this cost matrix. And the generator also uses a fuel curve. And you can see that the fuel efficiency is accurately modeled in HOMER Pro, with the fuel efficiency higher at high power output and worse fuel performance at lower power outputs. You can also put in maintenance schedules if you'd like to model those directly. Now the generator and component in HOMER is a very versatile component, and it's used to model anything that takes in fuel and returns dispatchable power and potentially heat, including fuel cells, microturbines, diesel gensets. And it can also be adapted to, for example, waste-to-energy systems or even geothermal. So now let's take a look at the PV component. The flat plate PV here, and PV means photovoltaic, it's using the optimizer. You can tell that by this orange star here. This lets HOMER Pro size the PV for you based on the PV size that minimizes the overall cost. If you like, you can instead explicitly select a PV size. So I'll turn off the optimizer and say, I could say put in a 10 kilowatt PV system, PV array in. However, in general, I like to use the optimizer where possible, in particular when I'm exploring options. So I'm going to turn it back on. Now, one interesting feature in the PV component is that you can model dedicated inverters. This includes things such as the Sunny Boy or In-Phase here. And you can also put the output onto the AC, if I click this, onto the DC bus. So I'm going to put it back on the AC bus. And you can also model here tracking, range of tracking options, as well as a range of tilts and slopes specified for your panels. And the HOMER software automatically does all of the calculations to help determine the PV output for each time step in the simulation. Now, the battery component. It can be used to model a wide range, storage component can be used to model a wide range of storage types and battery chemistries. The most commonly requested are lead acid. That's what we've modeled here. We've also commonly requested one is lithium-ion batteries. There's also various, let's see, flow batteries, as well as, let's see, flywheels. You can see we've got pumped hydro, supercapacitors. Largely any major storage technology you'd like to model, you can do that here. There are lots of batteries and storage components pre-modeled in our component library for you. But I'd like to point out that the battery that we modeled here, the lead acid, just like PV, wind, and the system converter, you can use the optimizer on the battery. And with this, to reiterate, HOMER will automatically help you determine the optimal number of battery strings for you. So I also want to take a minute to make sure to show you the grid component. Using this, you can model just about any utility grid you want. So we model simple rates with simple pricing, as well as real-time rates where the rate can fluctuate based on a price signal that you import. Scheduled rates based on, you can define any sort of rate schedule you'd like, as well as we do calculations around grid extension if you'd like to compare grid extensions. And within these, let's go back to scheduled rates, we can model unreliable grids, so here under reliability, as well as both energy and demand rates. And we have tools for demand limiting with lots of support for storage. So let's remove the grid from this model. And before moving on, I'd like to point out there's a large number of other components that we can model. But we don't have time in this session to cover them all. So you can look through these on this component ribbon. You've also got a lot of control over the various project parameters here under the project ribbon. So if we click on the economics, you can specify interest rates, inflation, project lifetime, as well as add system fixed capital and fixed O&M costs, in case there are costs you'd like to include in your model, no matter what system you're designing. You can also select just about any currency in the world. For example, US dollar, Turkish lira, they're mostly in there. You can also model various constraints, such as allowing some unserved capacity or energy, like we've done here with this maximal annual capacity shortage. And this, we specify here because this can be appropriate for smaller, particularly energy access projects like this community mini-grid. You'll also look down here and notice that we do model reserve requirements. You've also got the ability to include emissions prices, penalties, as well as limits, hard limits on those. So now, we've covered a lot of ground very quickly, but there's one last major feature I want to show to you. So I mentioned at the start that sensitivity analysis is one of the key analytical capabilities of the HOMER software. To do a sensitivity analysis, you simply have to click this sensitivity variable editor button. Let's do it on something that's really useful in this model, say the diesel price. If you click on the diesel price, you click the sensitivity variable editor button, and you can enter a different value. So you can see we originally optimized our design if the fuel price is $1 a liter, but what if the price were instead 50 cents a liter? Click OK, and you'll see that it says we've now got two sensitivity inputs, and click Calculate. And once it starts, you'll see that HOMER is running two optimizations in parallel, one for each of the two sensitivity values. And you'll notice that it does this through parallel processing. They're going at the same time. So if you have 4 processors on your computer, you'll be able to run in parallel 4 different optimizations. And each of these 2 optimizations that are running is for each of the 2 diesel fuel prices that we specified under our sensitivity inputs. So once you've gotten results, you can quickly compare the impact on your low-cost design if the fuel price is 50 cents versus $1 a liter. And by comparing these, you can see that the recommended amount of PV is higher if the fuel price is higher. That makes sense. It would reduce your fuel usage. The recommended amount of batteries is also higher. And you'll also notice that the total cost of your system is higher. So by performing sensitivity analysis, you can also get some powerful graphical outputs. To demonstrate this, I'm going to show you a great spot to explore other HOMER analyses that we've provided for you. To get to these, click here on the File menu, and click on Samples. And let's open a sample analysis for the Philippine village of Sicud. So we won't save our changes. And once this loads, the place I like to start anytime one of these loads is on the schematic. And you can see from this schematic that it's modeling a system that considers a diesel generator, a system converter, 2 different possible wind turbines, solar photovoltaics or PV, and a lead-acid battery to serve 1 AC load. Now when you click on the results, you'll see the sensitivity analysis showing various low-cost systems. So here it is here in the sensitivity. Here, I'll expand this down so you can see more of them. There's, for every sensitivity case, there's an optimal system. And this is one way to look at this system. You can also view these sensitivity analysis results graphically. Here, click on the graphical button. This will let you look at an optimal system type, or OST chart. And by selecting the sensitivity variables and values you'd like to look at, so let's say 0%, this will show you a plot showing what combination of components is lowest cost across the range of sensitivity values. Let's put the diesel fuel price on the y-axis and the wind speed on the x-axis. So now this OST shows you the optimal design at the range of sensitivity input values. So you can see that the diesel genset, looking over here on the right, DSL, is included in all of these systems. You can also see that PV is recommended in this system, and this system, or here on the upper left, where the fuel price is high and the wind speed is low. As the wind speed increases, these systems over here have wind. It's because wind is more likely to help reduce costs, so it tends to show up in the optimal designs here on the right. So with that demonstration, I'm going to switch back to the PowerPoint. Let's go to the next slide. So I'd like to thank you for taking the time to learn about HOMER Pro today. To help you get the most out of HOMER Pro, we recommend you play with the software during your free 30-day trial. It is fully featured and with all modules available to you. We also offer training courses that go into much more detail in this quick demonstration and help you to learn how to use HOMER Pro. They also give you an introduction to microgrids and distributed hybrid power systems, and help you learn how to perform your own analyses of these exciting markets. To learn more about that, go to gethomertraining.com. And of course, we are here to support you if you need help getting the most out of HOMER Pro.